Hi guys, welcome back to this video. We're going to continue our discussion on neutron damage. Okay, so in our last video we have discussed what happens when a neutron hits an atom. So we were doing a lot of calculation and we realized that we make a lot of vacancies and interstitials. So you have this neutron here, and it knocks onto an atom. We call this atom a primary knock-on atom, or pKa. So the neutron can either transfer some of its kinetic energy to this primary knock-on atom, which will then go on to knock on other atoms, or it can transmute the atom that is going to hit if the neutron is very slow. And the result in the former case, where the high energy neutron transfers lots of its kinetic energy into this pKa, is that the neutron itself will have a lot of kinetic energy still, since we have about 35 kilo electron volts. This should be a keV here. In our last video, it's supposed to be a keV. About 35 keV being transferred into this pKa at max. Oh, on average, sorry. Yeah, so on average, about 35 kilo electron volts are transferred into this atom, primary knock-on atom, and this neutron will still have many keVs of energy, maybe more than 900 keVs of energy, and it can still go on to cause more pKas. So that's what we discussed in the last video, and the neutron itself can continue going on to make more pKas. After knocking off this atom, it can still have sufficient energy to cause more pKas to be made. And we also note that each displacement that this neutron causes will cause a lot of Frankel pairs to occur, which is the vacancy and interstitials. So how much energy did this pKa have? The initial one we calculated. From our last calculation, we have about 35 keVs. Okay, let me shift that camera. I'll shift the paper so it's more clear. About 35 keVs based on the calculation where we use this vector, 1/4, or half times 4mm over m plus m squared, where m, the small m, is the mass of the neutron or the first body, and this capital M here, it's going to be the mass of the other body. So sometimes we call this factor here, we use capital lambda, which looks something like this, to denote this, because we don't want to keep writing 4mm over m plus m squared. Alright, so yeah, whenever you see this lambda in this video, do take note that it is this 4mm over m plus m squared that I'm talking about. Alright? So, based on this amount of kinetic energy available in this pKa, how many more atoms can it displace? So because this pKa has so much energy, 35 keVs, how many more displacements can we cause? Alright, so statistically speaking, when this pKa knocks onto another atom, sometimes we call it the secondary knock-on atom, or SKA, and this is the pKa here. Okay, we can use the same trick again, that the average energy transferred equals to half times the maximum energy that's being transferred. So that's the half of the lambda that we are talking about. So half times lambda times the energy of the incoming atom, that will be the energy that's being transferred on average. Okay? So we can then consider, alright, if this transfers half its kinetic energy to this, what we initially start with is this 35 keVs. Then after that, we will have two atoms having about 17 keVs. Alright, and this can still go on to knock more atoms. So let's say we have this first generation with 35 keV. So we have the energy here. So this energy, or sometimes I'll call it T, the kinetic energy. Alright, so the first generation you'll have 35 keVs. Second generation will have 17 keVs. Third generation, okay, it will be half of that. How did I get this the halving of the energy from each generation down? Now if we calculate, if we consider that this situation where one pKa knocks into another SKa, we can consider that these two masses are approximately, they're pretty much equal. So in this case, we can consider m equals to m. So the small m equals to big M, because this body, the first body, has the same mass as this. So that kind of makes things a bit simple. So let's calculate what our lambda is. Let me try and draw that a bit properly. So our lambda equals to 4. So I'll just use the m squared over 2 times m squared. Because m plus m, I'll just call it 2m, where m here is the mass of the atom. So 4m squared at the top and 4m squared at the bottom, that will just cancel out to give you 1. So you can see that in this case, lambda equals to 1, so half the energy is being transferred with each collision on average. So we can see that this generation of knock-on atoms will cause this cascade to happen. And we can keep going on, and then we'll have 4.25, for example. And you'll keep going on until a certain threshold, where the energy of each of the knock-on atoms is not enough to dislodge the next atom. So if this atom, okay, let's draw a new one. If this atom has a kinetic energy such that T is more, T is more than 2 ED. ED is the energy required to displace or dislodge the atom. So if T is more than 2 ED, what happens is that this iron atom or something like that will knock onto the other iron atom, and it will be just enough to displace it. However, when T is less than 2 ED, when T is less than 2 ED, the atom will not have enough energy to transfer to this atom to help it to dislodge, on average anyway. So let's obtain a relation for the kinetic energy of the pKa. So I'm talking about this. Let's have this relation for the kinetic energy of the pKa, or the knock-on atoms, as a function of how many knocks it gets when, on average, each collision will take about half its kinetic energy away. And this is, of course, a simplifying assumption, but it's a very helpful one. So let's see, we have kinetic energy. So if it's first generation, if it's first generation, it will be half to the power of 0. If it's and then let's say you have this, you're talking about the kinetic energy of this atom, which is also equivalent to the kinetic energy of this atom after the collision. So if you talk about the first generation, the primary knock-on atoms, so That's half to the power of 0 times T of the pKa. So we're talking about the first generation, which is talking about the first pKa. It's half to the power of 0. If we're talking about the second generation, it'll be half to the power of 1 times T of the initial pKa. So I'm talking about this pKa. When it so we can consider this the first generation, and then as it knocks on to the second generation, the pKa will have about 17 kiloelectron volts. So that's half to the power of 1 times the initial pKa energy. And then we can keep going. Third generation will have this much. And then you can keep going on to the nth generation. So T equals to half to the power of the number of generations minus 1 times the kinetic energy of the initial pKa. So sometimes you don't want, if you consider the generations like this, this will be the formula to use. Or else, if you don't want that minus 1 here, you can consider using the number, we just call it NF, which is the number of the number of times it knocks as well. So the first time, for the first generation, it has not collided yet. This pKa has not collided to any atoms yet. So we just call NF0. And this is 1, this is 2, this is 3. So equivalently, we can use T equals to half to the power of NF times T of the primary knock-on atom. So how many of these collisions are there? Okay, let me try and write that a bit nicer. How many of these collisions are there? T equals half to the power of NF times T pKa. So this is the original energy. This is energy after this many collisions. So how many collisions are there, so-called? So let's make this a subject by taking the logarithm, the natural logarithm, ln of both sides. So ln of T equals to NF times ln of half plus ln of T pKa. All right. All right, so how many collisions? We'll just make this a subject. So it's NF times ln of half is equals to ln T over T pKa. And then NF equals to ln half. So that's what we can get. And how many displacements will this pKa actually make? Well, all we have to do is have 2 to the power of NF. Okay, I shouldn't use that. Just 2 to the power of NF. And that will be how many displacements. So if we consider our table, number of displacements will be here. So the first one is 0, second one is or rather 1, because this is we can consider this a displacement. Second generation is 2, third is 4, because each of these can go and knock on another one. So fourth is 8, and so on and so forth. So you can see that 0 is 1 is 2 to the power of 0, 2 is 2 to the power of 1, 4 is 2 to the power of 2, 8 is 2 to the power of 3, and so 2 to the power of nf is the number of displacements we actually get. Alright, the number of displacements we get is 2 to the power of nf, where nf equals to ln t over t of the pKa, or ln half. So that's about it for that. But how do we get this t? Well, we can make use of the fact that when t is less than 2 ED, there will be no more collisions that happen. Okay, so at the nth generation, this is supposed to stop. So the threshold energy is kind of this value, 2 ED. Okay, so if it's more than 2 ED, it should stop. So if it's the energy incoming is more than 2 ED, it should stop. Less than 2 ED, it should not stop. So you can talk about this being the final threshold energy, which is let's say you have this 2 ED atom coming in, so that will be the last one already. So a knock-on atom with energy of 2 ED, kinetic energy of 2 ED, will knock on to this stationary atom. Both will have about energy of ED, and ED is the energy of displacement after that. Okay, so you can see that and this will be the threshold. So NF equals to ln T. Okay, I should write 2 ED over T of pKa over ln of half. So how much is ED again? We should remember that ED is about 25 to 35 electron volts. Alright, I'm trying to straighten that. Alright, so yeah, we can see that each pKa can make a lot of damage. So if you want to just punch in the calculator, 2 times say 35, the upper value, and each pKa we consider it having 35,000 electron volts over ln 2. So this is NF. Let's have our calculator out. So let me use Excel. I'm always more comfortable with Excel. So I'm just going to pull out the calculator. Anyway, while Excel is loading, let me go and simplify this first. Ln of 70 over 35,000 over ln of half. So let me try that. Ln of 70 divided by 35,000. Now this is an approximation. So in the numerator we'll have minus 6.2146, and the bottom is ln of half. The bottom is minus 0.693. So how many collisions do we have? So on average we'll have 8.9657 collisions. But you can't have 8.9657. Maybe you can round it down to 8. Now for now, for simplicity's sake, I'm just going to keep it on because it's an average number. Or maybe for simplicity's sake, we do that first, and then let's see how much the conservative estimate will get us. Okay, so let's get 2 to the power of this. So this is 500 pKa's or 500 displacement, and the other you have 2 to the power of 8. That's about 256 displacements. Alright, so either way it's going to cause a high level of damage. That's a lot of atoms to displace. Of course, the other one is where all of this double. Maybe in the reality, you have somewhere between this and this number of displacements. But yeah, in conclusion, we can see that this actually makes a lot of damage. So on a per atom basis, how many if you consider this on a per atom basis, how many what's the dPa, displacement per atom? Because displacement per atom, okay, so this is the way we measure radiation damage is called displacements per atom, for the simple reason of well, if you consider that there are many kinds of radiation sources, where there are lots of ways that this each sample can receive a certain amount of dose. So to kind of standardize the measurement of radiation damage, we use this unit here. Okay, so that is called dPa. Alright, so for now we have discussed how many atoms a single pKa can displace. So in the next video we want to ask how many pKa's a neutron can make on average. Okay, so thanks for watching. I'll see you in the next video. Bye bye.